Hello and welcome. This is the sixth video in my counters series, even though part 5 effectively had 2 videos. But this is the sixth video, this is the sixth part. And in this video, what I want to do is to present the counter, but present it this time as a state machine. If you remember, when we were coming up with a structural architecture for it, we had a truth table where we had a present state and next state. So if we had present state and next state, it makes sense that a counter is a state machine. And that's what we'll do in this video. Now, instead of writing out the code while recording the video, I've taken the liberty of writing the code ahead of time so that this video will be significantly shorter than the previous ones. So here we are in our code. Entity, I'm calling it sync counter 3. Every state machine is synchronous in nature. So it's also a synchronous counter, but yeah. So I call it sync counter 3. And here, first thing I did was to define a state type. Now, the various state types I have here are 0, 1, 2, 3, 4, 5, 6, 7. That's the individual states of the counter at any point in time. Now, do you have to define a counter as a state machine? No, but the whole idea of this video is to serve as a prelude to state machines, which is in the next video. So a counter, to a large extent, is a state machine. Why might you want to define a counter as a state machine? There's one big reason why you might want to design a counter as a state machine. One, and that reason is, if you design it as a state machine, to change the order in which the counting is going, the sequence of the counts, you could change that easily from this architecture. You don't have to go through a long process. So if you were using the structural design and the structural architecture for the counter, and you wanted to change the sequence of the counting sequence, suddenly you will have to go through a truth table again, do your logic minimization, write a new architecture entirely for your counter. However, with state machines, all you will need to do is to simply change what state goes to what state, and that is that the compiler, VHDL compiler, will figure the rest out. So these are the types of the states, and then I've also set a present state, a next state. Generally speaking, for state machines, you could take this as a standard. To a large extent, we often will define a state type and then have a signal that has a present state and a next state. Do you have to have these 2 lines to make it a state machine? No, you don't have to have them. You don't have to define a state type. But it's a lot more convenient to define a state type and then to have signals that are of type state type. If you want, you could initialize this. So for instance, I could initialize this to 0. Now, what is 0? 0 is one of the state types, so it will understand this initialization. Okay, let's go on. Now, here I've divided up my state machine code, the architecture, into 3 processes. The first is what controls the state, what makes it go to the next state, or what clears it or sets it, as the case may be. So what makes it go to a particular state? In other words, yeah, think of it as, in this case, when rising edge of clock, it will go to the next state, whatever we define as the next state is. So what makes it go to the next state? That's the first process. The second process is what is the logic of going from one state to another. So sorry about that. So what's the next state logic? That's what you have inside this process. So when you are in one particular state, what's the next state it should go to? Okay, when you're in one state, what's the next state you should go to? For a counter, really, what's in the present state, the next state is just the next count it wants to go into. So like I said a little earlier, if I wanted to change the sequence of counting, all I need to do, literally all I need to do is to change this. So for instance, from 0 I'm going to 1, from 1 I'm going to 2, from 2 I'm going to 3. If I want to change the order, all I need to do is from 0, where do I go to? Specify it here. From 1, where do I go to? Specify it. From 2, where do I go to? Once I specify all of that, literally compile and redeploy your counter, and it will count in the new sequence that you have just specified. Finally, the third process I have there is the output logic. In other words, in each of these states, what gets displayed to the output. Okay, so when 0, I've left something out there. When 0, I'll just copy this and paste it there, so I don't have to type that. When in state 0, then output all zeros. When in state 1, output this. When in state 2, output that. And so this is what determines what goes out in each state. Next question, do we have to have 3 processes? No, you don't. For example, we could have taken this all off. In fact, no, from here. We could have taken all of this off. Sorry, let me just comment that out. I could have commented all of that out, and just on rising edge of clock, check the present state. Whenever the present state is whatever, then I won't say next state is this. I'll say present state is now, will now become 1. So on the rising edge of clock, that will go. So it will work perfectly well. The counter will work as it should work. However, dividing it up in this way makes it such that if you wanted to change, for example, the next state logic, the sequence in which the counter is going through, you won't have to worry about breaking some other parts of the code. All you need to do is just literally is your next state logic, deal with this process, make your modification in this process, and that is that. Your output logic, you don't have to worry about it. Your transition logic, you don't have to worry about that. So you could just leave this logic, leave that logic, and modify the one you want. If you wanted to modify the outputs, then just come to the output logic and modify what goes on in here. So dividing it up into 3 could serve a very beneficial purpose, at least for modularity and for ease of management of your program. So that is the architecture here. Now I just mentioned, I mentioned earlier that if you wanted to have a different sequence, all you need to do is just change your next state logic. So what I've gone ahead to do is, this is a binary counter. It goes 0, 1, 2, 3, 4, 5, 6, 7. There is another type of counter that we know that is called a gray counter. A gray counter is one in which when the counter is going from one state to the other, only one bit gets changed, only one bit gets flipped. So, for example, you could have a sequence that goes from 0 to 000 to 001, then to notice from 000 to 001, only the LSB flipped. 001 to 011, now the middle bit flipped. 011 to 010, now the LSB flipped again. Then we flip just the MSB and we get 110. Then flip the LSB again, you get 111. Flip the middle bit, you get 101. Flip the LSB, you get 100 and then 000. In each case, just one bit gets flipped. So this is a gray counter. If we wanted to define a 3-bit gray counter, we could literally just copy this entire architecture, or we could modify this architecture, but we could copy this entire architecture, paste it, which is exactly what I did. I copied the entire architecture. Now I changed the name of the architecture to gray counter, and this is exactly the same as you had above. Next state logic is what is different. From 0, we go to 1, that's correct. From 1, we go to 3. Remember this sequence here. From 001, we go to 011. Then from 011 to 010. From 3, we go to 2. And this defines the sequence we're interested in. So this next logic state was modified. This output logic state remains exactly the same. Nothing changed in it. Okay? So that is how easy it is to modify the order, the sequence of the counting. So let's go ahead and test this in a test bench, just to see that it works. Okay, so what I have in here is gray counter. Let me make it binary counter. So I'm going to test the binary counter and then run all of this. So I'll test the binary counter. Let's go ahead to model sim and compile this. I've changed, my current directory is the sync counter 3. So I can just go ahead and hit my compile button and I'll find the contents of sync counter 3. So sync counter 3 compile. Work library does not exist. Yes, go ahead and compile it. No errors, no warnings. That's good. Compile the test bench. Done. Let's simulate the test bench. Sync counter 3. So test bench, we're simulating this. Okay, so it wants me to escape. Sorry. Add wave. I'm going to simulate this for 100 nanoseconds. Run the simulation. I'll make this, let me zoom out just a little bit so we see what is going on here. So if I scroll to the start, you see it starts from, I could zoom in just a bit, so we'll see the very first state. The very first state 000, and then it goes to 001, 010, 011, 100, 101, 110, 111. Normal binary counters we're used to. Again, your set and reset still work the same way we expect it to work before. That's perfectly fine. Okay, so this works like we expect it to work. Let's go ahead and simulate the gray counter instead, and just see that just by changing your next state logic, everything changes. So I'll come back here, compile just the test bench. So I compile my test bench, done. if I come back, let me just come back to the library just for a moment. If you checked in here, see your sync counter had two different architectures. So just to mention that is there. But again, this is our synchronous counter. This is where we're in. We're in the simulator. So I'll just reset. Since I've recompiled, I'll reset and run this all over again. Now scroll back to start 0001 now 011 before 010 and then 110. This is your gray counter. This is the sequence we defined, and see it works as we expect it to work. One last thing, let's go into quarters, and what we'll now try to do here, this sync counter 2, let's see, you have sync counter, okay, so sync counter 3 is open. I'll go ahead and compile this, and what I'm interested in seeing, okay, so I should have just hit analysis and synthesis, but sorry about that. Now, all I'm interested in seeing really is seeing the summary. I want to see how many logic elements it uses for this. Now, if you remember for sync counter 2, let me pull up sync counter 2. I don't know if we still have the report here, view reports. Okay, yeah, so for sync counter 2, we had 10 logic elements. Oh, it's going to still compile it. However, we had 10 logic elements, okay, and 3 registers. So, once this is done with this, I think I'll probably just go ahead and stop this with the hope that it will not delete the entire flow summary. Okay, so I'll stop this. So we see our flow summary, yes. Now we use 18 logic elements and 8 registers. Now this is the case because we have made it a state machine. We've made a state machine, so we're using significantly more resources for a counter, because a counter, so when we had just this is our best implementation when we just used unsigned to increment, or standard logic or integer to increment. In this case, we had just 10 logic elements, 3 registers. But when we used a state machine, then we have 18 logic elements and 8 registers. Same number of pins were used, I/O pins were used, but we used more resources within the FPGA. So are state machines bad? No. State machines may be an overkill, but they help us very well, because generally speaking in life, we used to state machines. We use state machines a lot. So they may not necessarily be the most optimal code to, or most optimal way of coding a particular system. However, they will give you a system that will be much easier to debug and probably much easier to specify once you're used to state machines. So it's a very good idea to work with state machines. That's it. I think that'll be it for this video. In the next video, we will take a state machine example, one that properly should be coded using state machines. Could it be coded without state machines? Yes, but it will be a whole lot easier to code with a state machine. Specifically, we'll be working on a traffic light controller in the next video. See you in the next one.